Hey guys, so hopefully the pre-lab exercise went well. If you're watching this video, then you've kind of figured that part of the assignment out and we're to the actual titration portion of the lab. So what I'm going to do is I'm going to demo the titration for you and just kind of go through the various procedures that you need to watch out for. Some of this stuff will be review from Chem 20, and that's okay. This stuff you need to know for Chemistry 30 as well. So a couple of things I just want to point out in terms of materials and materials lists. First of all, we've got a 50 milliliter burette here with a stand and a clamp that I've set all up. Inside of the burette is my titrant. This is potassium permanganate solution. So it's a solution of potassium ions and permanganate ions if we're making our list of species present, which you would have done in the pre-lab exercise. Also, I've got a small 125 milliliter Erlenmeyer flask. That's going to go underneath of here when I do my titration. I also have my solution of iron 2 ammonium sulfate hexahydrate. That substance is quite a mouthful. So for the further on into this video, I'm just going to refer to those crystals as iron 2 sulfate. But in the pre-lab exercise, what you would have calculated is the mass of the crystals that you would have needed to make this solution. And so in the procedures, you can see in the assignment that I've posted that and in the pre-lab exercise, you would have calculated that you would have needed 0.981 grams of the ammonium 2 sulfate crystals. And what you would have done with those crystals is you would have dissolved them, and I did this already, as you can see. I dissolved those crystals in about 20 milliliters of sulfuric acid. Just means that those crystals are now in the presence of acid, or they're in an acidic solution. And then I carefully measured that solution to be exactly 50 milliliters by just adding whatever water I needed to bring that volume up to exactly 50 milliliters, so that I could get the desired concentration that was asked for in the pre-lab exercise. This solution right here is going to be my sample. Now I'm not going to titrate the entire sample. What I'm going to do is I'm going to use this pipette and this pipette pump to pipette out 10 mils for each trial that I'm going to do. And so I'll show you how that's to be done in just a minute. But before I get started, what I want to do is I want to make sure that I fill the tip up of potassium permanganate solution and then make my initial reading on my burette, so that when I do the first trial, I know when I make my final reading on the burette what those two numbers are, so I can subtract them and figure out how much of the titrant I used. So when you do this, you just need to do it really slowly. You open up the valve just a little bit, and then you can see that the purple will slowly go through, and this just makes sure that all the bubbles in the tip are out, so that when you're actually adding potassium permanganate solution to your sample, that when the numbers drop here, it corresponds to the fact that you've actually added something to your sample in the trial that you're doing. So I don't need this anymore. I can wash it out later. So what I'm going to do now is I'm going to pipette out 10 mils of my sample. This is the this is the iron 2 ammonium sulfate hexahydrate solution. Making sure that when you are doing your measurements here, that the bottom part of the solution is touching the line. Along the sides of the glass, you'll notice that the solution is a little bit higher, and it's sort of curved like this. So you want to measure at the very bottom of that bubble when you go to make that measurement, so that your results are as accurate as possible. I'm not going to use that pipette anymore for this trial. Here's my 10 mils inside of my beaker. This is my sample, and I'm going to perform the titration. So what I'm looking for here when I do the titration is I want to look for a persistent purple color that's going to come out of it. Now you notice I'm going to start out with a clear solution, and then it's actually going to start to turn a little bit yellow. and that's because of the ions that are being produced from the redox reaction. And if you go into your data booklets near the back, you'll notice that there's a table in there that shows how or what the colors are of certain ions in solutions. And if you look at the iron ions in that table, you can see that one of them is sort of a little bit of like a yellowish color. So I'll let you go into your data booklet and you can check that out. So when I do this titration, I'm just going to add some stuff in, and when I add a little bit in, you can see that it disappears. When I add a little bit more in, then it disappears. All this means is that the potassium permanganate that's being added in, the reaction is occurring and it's starting to make some of the products. The point of a titration here is that I want to completely react all of the iron ions that are in here with the potassium permanganate solution, and I want to find out when this entire sample has been reacted. That way I know stoichiometrically that the reaction is finished, and then I can perform some stoichiometry to calculate what my unknown concentration of potassium permanganate is up here in the burette. So I'm going to stop the video. I'll get close to the end of the titration, and then I'll show you what it's supposed to look like just prior to reaching the endpoint and reaching the endpoint, and then if you burn the solution, what does that look like? Okay guys, so you can see I've recorded my initial reading on my burette before I started. It was 32.2 milliliters. Here is the solution, and I'm close to the endpoint. Here you can see obviously that this is like a very yellowish orange type of color, and this is indicative of particular ions that are found in this solution. And so if you look at the balanced redox reaction that you did in the pre-lab exercise, you can see the different ions that are made from this reaction, and go into your data booklet and see if you can find any of those ions in your data booklet and what color corresponds to them, and see if you can find any one of those ions that matches this color. When I get close to the endpoint, what I want to do is I want to add titrant here drop by drop, because I want to be very precise. And so I'm just going to add one drop, and then I want to stir it around. And when I get a persistent purple color, then I know that I'm finished. So you can see that purple is still disappearing. It's getting close, but not quite there yet. And so that's a really, really like almost dark red, starting to get quite purple type of color. And so I might just look at this number here and record, okay, this is 36.9 milliliters. Maybe this is the final. Maybe this is the final endpoint that I've reached. If I add one more drop and that purple doesn't go away, then I know that I've burned that solution. And so I mix that up, and that is definitely a lot darker. So I think I would like to stop there at that 36.9. If I add a couple more drops here, just to show you what a burned solution looks like. Get that other one to fall in, and you mix this around. You can see that that purple mixed with that red and orange kind of gives you that deep reddish orange color, and that's beyond the point of where we've gone. So we know that we've reached the end point now, and what I'm going to do now is calculate what this number is that tells me how much of the titrant I actually use. So if you subtract those two numbers together, you can see that this is just 4.7 milliliters of the titrant that was used to completely react the iron 2 ammonium sulfate hexahydrate solution that we had started with in here, the 10 mils. And so what I'll do in the next clip is I will show you the balanced redox reaction that you would have had from the pre-lab exercise, but in addition to now, how do we do the stoichiometry associated with this redox titration to solve for the actual problem that we were presented with at the beginning, which is what is the concentration of the potassium permanganate. All right, so we're back with the end of our titration lab. What you can see here is I did the other 2 trials and got some numbers for you guys. And this is what you would see on a titration type of question as it relates to the data that you're given, and then what are you supposed to do with that data. So you might be given a table, something like this, where you're given 3 trials with these numbers, and then you have to calculate how much was used. Now we did that for trial number 1 already. And if you plug this into your calculator, you should just get 4.7 milliliters. All you do to get that number is you go 36.9, subtract 32.2, your final reading minus your initial reading. That tells you how much you used. Do this for the other 2, and you can see that these numbers end up like that. Now, what you have to make sure that you're doing with any titration is that you have to make sure that you have 3 trials that are within 0.2 milliliters of the other trials. And in this case, you can see that I've got 3 trials that fit that. I've got 4.8 here, and 4.7, 4.6, 4.6 and 4.8 is 0.2 away, so that fits the rule there, and comparing all the others do that as well. What are we supposed to do with these numbers though? What we're supposed to do is, once we have our 3 trials that are within 0.2, you have to average those numbers. And so if we average these, 4.8 plus 4.7 plus 4.6 divided by 3, you can see that that gives us 4.7 milliliters. And you probably don't need a calculator for that, but you can plug it in if you need. There's our average volume for the 3 trials. Now this is the number that you're going to want to use. If you take a look at our balanced redox reaction over here, you can see I've got it set up to do some stoichiometry. And without this number, you can see that we don't have enough information to do the redox stoichiometry here that we need to do. You can see that we're missing this number. And so this is the point of doing a titration, is when we do a titration, what we're trying to do is we're trying to figure out what is this number. And that's what we did. Notice that it's the volume of the permanganate ions that we were using in the titration. That was the purple stuff, the titrate in the burette. And doing these 3 trials just ensures that when we're doing the trials that our results are fairly consistent and that we don't have a wide range of variability within our results. It makes our results a little bit more reliable when they're close like that. And so we take the average of these 3 trials so that we're incorporating all of our work into one single calculation. And so I take this average of 4.7 and I plug it in here into my setup so that I can do my stoichiometry. And now you can see stoichiometrically we can solve for the unknown concentration of the permanganate ions, or in other words the potassium permanganate solution. And this is a very common type of question that you can see in the redox unit as it relates to redox stoichiometry. So we do this titration, we've got the results, we plug it in here, let's do the math. So here's my given. You can see I've got my required and my given labeled out. And so 10.0 milliliters of Fe2 positive ions. Whoops. Plug in my concentration here, moles per liter. My mole ratio is 1 mole of MnO4 minus to 5 moles of Fe2 positive aqueous. And my final number here, which is the volume of my permanganate ions, is 4.7 milliliters. Now, looking at my units here, I want to just ensure that my units cancel out properly. I've got moles canceling out. I've got my iron ions canceling out. I want moles per liter as my final unit here. That's what concentration is described in terms of units as moles per liter. And so I just need to get rid of these milliliters. So to do that, I'm just going to take these milliliters and put them on the bottom. And so I'm not changing my answer or anything like that, I just multiply that by 1. So 1 over 4.7 milliliters, and then my milliliters cancel out as well. Plug all that into your calculator and you end up with an answer of 0.0213 moles per liter of MnO4 minus ions. Hey guys, just wanted to point one thing out from the end of our last video that I failed to mention, is that if you look at our balanced equation here, if you remember, I asked you to go into your data booklet and take a look at the colors of common aqueous ions. And you can see those all right here. This is on page 11. And this table right here, if you look up iron 3 positive in this table, so the iron 3 ion, the color that it says that it's supposed to be in solution is orange yellow. And if you remember from the previous video where I was titrating the iron ammonium sulfate solution, that solution was starting to turn this yellow color, and then as it got a little bit more concentrated, it turned into this orange yellow color. And so I just wanted to point that out to show you that that's an evidence, a qualitative evidence, one that we would observe, is what that means, that this reaction was going and occurring the way that it was supposed to, in the way that we predicted in our balanced chemical reaction. So this here was the orange yellow color that was showing up in that solution as that titration was progressing. So hopefully this was helpful and you're able to get the information you needed in order to know how to do redox titrations and just titrations in general. So thanks for watching, and we'll see you guys in the next video.